Thanks, everyone. It's great to be here. As I've kind of hinted at, I would love to start with just understanding of who's in the room because every talk is very different. And we had some great talks earlier today on deep learning, so hopefully you've had some background in it. But still, I think it's good to double check so that I'm not, talking too far ahead or something that's too basic and boring for everyone. So can I just get a show of hands, really nice and old-fashioned, like who here has like actually trained a neural network, like in their own environment, something like literally copy-paste from some tutorial. Okay, so about 30%. Yeah, like MNIST, whatever, all these things are fine. Who here like would say they're like comfortable at least knowing all the concepts of deep learning? Like, stochastic gradient descent, things like that, okay? Interestingly, that seems like fewer people than the ones who've trained. Okay. Okay. Who here knows what a GAN is? Okay. And who here has trained a GAN themselves at any point? Okay, one person. Cool. So the rest of you, so about 40% I think have some background. The rest of you, I guess, are maybe in the wrong conference. So we'll start quite basic, and then hopefully it'll become clear. I don't know if that's if you guys want to ask a question even in between, if it's like really not clear, I'm happy to do that. Otherwise, obviously, there's time in the end for you guys to ask anything. Okay, so without further ado, so basically a little bit about myself. I was working in computer vision for the last couple of years. Before that, I was at Modano in R&D. I was working at Filter.com, Pearson. Taught a couple of universities, also have some background in startups. In the meantime, I wrote this book. Oh, by the way, I have some promo codes from the publisher to give away. So if you wanna, if there's anything from the talk that you find interesting or relevant or just like noteworthy of any kind, post it on Twitter or LinkedIn. And tag me, and I'll do a raffle where 2 of the free, I think they're ebooks, I'm not 100% sure. Either the ebooks or the physical codes, and I have 2 to give away. So I'll give 1 on Twitter and 1 on LinkedIn. So if there's anything interesting, take note and tweet at me or whatever. 2 of you will be the lucky winners of the book if you're interested. Okay. So without further ado, what are we going to talk about? So first of all, touch on sort of unsupervised machine learning and the differences between supervised and unsupervised. When we'll talk about why generation is hard, right? Like, why is this an interesting problem from sort of mathematical point of view? And then we'll talk about, what's the basics of GANs, about some popular architectures, something that's related but not exactly about GANs, but it's still worth talking about, which are adversarial examples, and then some practice and Q&A. So, okay, so we have supervised machine learning. We've heard a couple of presentations that already use that, but just a super quick recap. You have some sort of input data that could be like text, images, whatever. You extract some feature vectors, which typically a neural net would do for you in this day and age. But of course, if you're still using some more traditional machine learning, then you would probably have to do that yourself. You take some labels, and this is the important part. You kind of mesh them up in the machine learning algorithm, and out comes the predictive model, right? Now, at inference time, which is when you're actually trying to get something useful out of your model, you'd start with text, document, images, whatever. You extract the same feature vector, run through the predictive model, and get an expected label out of it. Now, why is this, relevant? Well, you need to have these labels that are super key to making this all work. And that's where the supervision comes from, right? Like, you have the key component without which you cannot really start. So a lot of people, including the really nice designing neural architecture talk just a couple of moments ago, talked about the importance of having labeled example. And that's the bottleneck to most of deep learning these days. Now, what is even generative modeling? Well, first of all, it's unsupervised. So here we have generation of MNIST, which is like the hello world of computer vision. It's really basic example of where we kind of take single handwritten digits in 28 by 28 pixel resolution, and we kind of try to, originally labeled for which label it is, and then you try to predict which label it is. Now, of course, in unsupervised machine learning, and when you're trying to generate these examples, you don't really need that. You just try to generate a distribution that looks similar or exactly the same as the original data distribution. So this is actually a process of like sort of iterating through the data, starting from random noise all the way to something that looks like digits, right? But you don't need the labels because you're just trying to mimic the distribution based on the distribution itself. Obviously, it's still machine learning, so here you can see how we start with some bad approximation, which is noise, and then improve over time. So these are just different epochs as we go through the training process. But of course, some challenges that come with the absence of labels is how do we know how well we're doing? Because we can't measure metric in the traditional sense. We can't measure RMSE or loss functions or whatever. Like, they're not as simple. In the end, we just kind of, in the early days of generative modeling and GANs, people just like looked at the examples and said, does this look good or does this not look good, right? And it was like a very bad metric. Like, usually one wants to have something that you can quantify. So why is this so difficult to quantify? Well, the distribution can be quite complicated. So this is actually projection, like principal component analysis of the same MNIST data set. So same handwritten digits modified from 768 dimensions down to 3. But this is still really hard. Like, I don't really know like what. Okay, so I guess I can tell that they're clustered, right? Because the colors mean different labels. But I can't really say like, is this where the 7s are or the 3s are or whatever. It's very hard for people to reason at this level, either in the reduced 3-dimensional or even in the full 768-dimensional data set. Like, we can't really reason at that level of dimensions. We can reason in 3 kind of, and beyond that, it's just over our heads. So the distribution is complicated. The evaluation can be complicated too, right? So it's not trivial to say like, what is a good 3? What is a good 7, right? Even if we're sticking with a really simple example. And one of the innovations of GANs is that they model this complex relationship implicitly. They try to understand, okay, like out of this massively complicated function, where in that space does do the good examples live, right? Like, and basically, rather than having some like neatly written analytical formula, you just get some like implicit understanding of where good examples live. So what are GANs? So there's really, like, if you break it down, you already get like halfway there. So networks, so there's 2 of them. There's the discriminator and there's the generator. So the generative part is basically captured by the generator, and adversarial is because they compete against each other. The generator, what it does is it takes some noise and then just some latent vector. Basically, you sample 100, like you roll a dice like 100 times or whatever, and then the generator uses a series of operations to create examples similar to the original data set. And then the discriminator just intermittently gets data from either the real world or from what the generator has generated. So for the discriminator, it's literally just a binary classification problem. You have to classify as like which of those 2 streams it is. So that's like well and understood. It almost has this like implicit label of real or fake, right? It's binary. Whereas the generator, the problem there is much more complicated. You sample from some random numbers just so you don't generate the same thing every time, and then you propagate that through and you try to come up with something like this. Well, how well are you doing at that point? Well, that's where the discriminator's feedback comes really useful, because if you're fooling the discriminator a lot of the time, you're obviously doing something right. And you can sort of improve based off the backpropagated error, and as a result, you can kind of see which direction to go to if you're not doing so well. So at least you have feedback to where to go. So just a quick like recap to have it all in one table. Just generator gets a bunch of random numbers, creates fake examples that strive to be as convincing as possible, and then we generate some fake data that's ideally indistinguishable from the original data set. And the discriminator basically just gets data from one of two sources and outputs the likelihood that the example is real. And the goal is to just distinguish between the fake examples coming from the generator and the real examples coming from the training set. So an analogy to think about this is just like, imagine you're like a forger and trying to forge like a Da Vinci painting, right? You get some inspiration, which is the latent vector. Then you try to draw something up, and you ship it off to like an art gallery where they have like a detective or a critic or someone look at it and say, this is crap or this is real. And then they, through that you get some feedback, and then you can improve for next time, right? And maybe next time you do something that's much closer to Da Vinci painting, so they accept it, but then people come to the gallery and say, obviously this is not real, so they get the error, the increase in their loss function, right? And they have to sort of go back and reevaluate, sort of learn a bit more. So the key point here is that this is all iterative, right? Like both networks, both the generator and the discriminator start with being quite bad, but they improve over time. And this is really important as a sort of learning mechanism, because obviously you're trying to model potentially quite complex distributions. So you kind of have to go around a couple of times to really like nail where the real examples live. Does this make sense so far? Sort of? Yes, okay, good. So, I mean, there's some numbers just to scare whoever might be in the room and doesn't feel scared already. It's not that important. All I'm going to say is that, so there's the two loss functions, right? So one of them is the generator loss function, and one of them is the discriminator loss function. So here, all I would highlight is that there's the portion for the real data, and there's the portion for the fake data. So you have basically, for those who are familiar, like binary cross entropy loss, and you can kind of treat it as a regular supervised problem. But the key thing here is that the two loss functions are literal opposites of each other in the original formulation. So they have actually like competing very directly against each other. So one of them has to lose for the other to win, which might remind you, for those of you who have brushed into economics of game theory, and that's kind of exactly what it is. Indeed, the original paper kind of does talk about the connections to two-player games and Nashville equilibrium and all these neat things that help it get the initial theoretical grounding that kind of made it accepted in the academic community as something that's not just like happens to work, but they sort of gave them important theoretical connections to why is this why should this even work from a theoretical point of view. So just one last analogy. This is a really good sort of schematic, I think, from a paper that tried to connect Metropolis Hastings MCMC to GANs. It's not important. I think all that this is saying is that imagine if you have some loss function, like some hilly environment, right? Like normally stochastic gradient descent, you try to go downhill and try to minimize the loss and go in some like local minima. But now you have two players and they compete against each other. So they're trying to basically, one of them is like trying to go uphill and the other one's trying to go downhill. So it's like a slightly more formal way of thinking about what's going on. In the end, people actually started not using the original game theoretical loss function, but they just made this one adjustment. The first one is exactly the same. And the second one, they just kind of added the different component for numerical stability. Usually this is still a loss function that gets used today. There's other propositions that are slightly better in some scenarios, but this is generally still a good loss function. All that this is doing is now it's kind of, they're still directionally against each other, because if you kind of multiply that out, you actually still get this competition, but it's not exact opposites. So it's just that to be aware of that, now people use slight improvements on the original proposal. And this was actually even in the original paper. It just turns out that it generalizes much better. So why is this an interesting problem? So we spend a lot of hard work trying to understand all these complicated equations and processing the dynamics. Well, one of the reasons is that generative modeling has largely been unsolved. We have had many successful examples of supervised learning, but not so much of unsupervised, and definitely not of generative learning, right? So now we're moving closer to unsupervised learning as a sort of workable paradigm where we can actually take some of these techniques and apply them in the real world. And typically, like something like a variational autoencoder, which is the example that you see here, that was like the best we could do in about 2016. So not that long ago when you think about it. And these images, they look okay. Like they're obviously human faces, but they're like far from where we could be. And there's many different domains that you want to generate in, and I would even say that GANs are probably the first general-purpose generative framework that you could use that actually leverages machine learning. So where do we get to now? So this is one of the first papers that demonstrated full HD resolution of human faces that are all synthetic. So none of these people actually exist. In fact, if you go to thisisnotarealperson.com, slightly more advanced version of this network is generating a new face every time you refresh the page, just from a slightly different architecture called style GAN. This is from progressive GAN, doesn't matter. But you get people that are photorealistic in beyond full HD nowadays. So you get absolutely like complex, super complex functions that now we're able to replicate just by feeding it a bunch of human faces. And because this is all unsupervised, you don't need any labels. You just need to like scrape a couple of images of a Flickr or whatever, and you can generate this. So I mean, pretty faces are good and all, but why is this? What are some of the like next things that we can apply this to? So one of the applications I'm personally most excited about is something called CycleGAN. So this is basically a domain transfer network. It uses much more complicated architecture, but it basically leverages cyclical loss. So we'll talk about that in a second, but just to motivate a little bit, because I know that this has been a lot of hard work so far. So where do we get from something like that looks like a Monet painting into a photo, or from photo to Monet painting? Like these are the types of transfers that you can do when you have a generative model that understands the two domains, right? So you can take something that's a picture of a zebra and transfer that over to a horse, or from horse to a zebra, and it actually like understands that, hey, this is grass, so you probably don't want to change that, but this is clearly the horse part, so you probably want to change that so that this bit gets recolored as a horse, or the other way around. Same way, one other example is just like summer to winter or winter to summer, or you can propagate this to many different styles. Same way as style transfer for those who are familiar, but this is now a much more general problem specification, and it can definitely do things that style transfer can't do, right? Like summer to winter is actually not a trivial problem, because usually you have to modify, if you have like not just put snow on the ground, but also like put bits of ice into the river and so on. So it's a much more complicated problem, where style transfer doesn't work anymore. Obviously, this architecture is more complicated, and there's even further extensions. But there's a lot of like sort of underappreciated work still. Like this is still a very new field. Like this paper originally came out in 2017. And there's still improvements that are to be made that haven't been like really tried. So this is still very much an active area of research. So how do we get to that, right? Like that's maybe an interesting proposal, but how do we get to that? Well, so you can start with the two domains, like summer and winter, A and B or whatever, and then you can basically have one generator network going this way, and another generator network going the other way. So you basically create a loss where you like start with the domain A, go into B, like basically try to reconstruct an image in the B domain, so let's say winter, and then you try to make it summer again. And then because you have the reconstructed summer and the original summer, you can measure the loss between the two, right? So you kind of go one hop and then back, and then you measure the loss. And this actually gives you a super important sort of link between the two domains. So you can say, okay, like I don't actually need labeled examples, because there were original versions of this was called pix-to-pix and actually needed like a full description of the image. Really complicated, really hard to get. Whereas this just said, forget about that. We'll just start from one domain, go to the other one, and then go back. And that's how we'll get the last missing component in the loss function to actually make it not just realistic, but also like consistent, like make the cycle consistent. So an analogy you might think of is like if you have a sentence in like Lithuanian and then you translate it to English and then back again, you ideally want to get the same sentence, right? So this is kind of the similar idea. And if you don't get the same sentence, then you can measure the loss and see what went wrong. So this is just that, except on a pixel level and much more complicated. But we still have discriminators. So here you get some sort of input. This is apples to oranges because everyone wants to compare them, right? So you just get an input. You still evaluate the discriminator. So you still force one of the discriminators. There's two now, to make the initial guess. Like, is this real or not? Which obviously should ideally say that this is real, but if not, then you get at least useful feedback. Then you try to translate it once into oranges. And again, you get a second discriminator, which should tell in the domain B, is this real or not? And then you translate it back, and you get the reconstruction loss that we talked about. So obviously, this is one of the more complicated architectures, just on the basis that you don't have, some of you might be used to one neural network. Here you get 4. So, there's obviously a lot more stuff that's going on. But as a result, you get some interesting applications. I'll mention just one more cutting-edge application, something called BigGAN, which was released, I think, 2018, but was only presented at iClear this year. And actually, all of those images that you can see in the background, all of them are synthetic. They're all random walks through this latent space. So all of these, like eagles or birds, or they're all made up by BigGAN. So the level of visual fidelity and the richness of the environment that it can capture is going up really exponentially. So why is BigGAN noteworthy? So it was created by a DeepMind team and presented earlier this year at iClear. It generates like 512 by 512 images of all 1,000 classes of ImageNet. So if you know ImageNet, that was the competition that really kickstarted this deep learning revolution. It was the first network where we allegedly got superhuman performance in object recognition with AI compared to regular people. And it's actually quite a complicated data set when you think about it. It has 1,000 classes, as diverse as like everything from wolves, mushrooms, space shuttles, coffees, whatever. All of these are synthetic, by the way. Everything you see here. So you get massively complicated, sort of networks that can generate really powerful images that still look very convincing. I mean, if you're kind of used to looking at those images, or if you stare at them hard enough, you can kind of see there's weird things going on, right? There's obviously things around the edges of this coffee cup that don't make it quite real. But at the same time, some things are really hard. Like this bubble looks really good. Equally, the mushroom or the spaghetti. I think I couldn't really tell. Like I don't really know. The other things, I think there's some indication of there's things that are going that's a little bit weird. Equally around the edges here. But at the rate that these things are going, this is only a matter of time. And remember, this is already like a year ago. So there's obviously improvements are already being implemented. There's papers already building on this paper. People have started using that in their machine learning pipelines. So they have actually started implementing parts of this into production and so on. Also, one of my friends wrote this really interesting ArtBreeder application, which is basically all of these, again, are different samples from the same trained network that you saw on all these slides earlier. And these are basically just random walks through latent space where people try to create art by basically breeding different latent vectors and then combining them in interesting ways, or trying to mix and match or adjust slightly the latent vector and so on. It's actually really intuitive. Like, you can, and anyone can use it. You can just create similar or more diverse images. It's great. I recommend to check it out. You can just kind of play around, create some interesting free art infinitely. But all of this got people thinking about the notion of adversarial examples. So obviously, we now see that there's this concept where you can kind of fool a network into thinking something is real or not, or sort of making it misclassify. And actually, that poses its own challenges. So when you think about a lot of computer vision, one thing that people maybe don't talk about enough is that there is this thing called adversarial noise, where if you take something that's like an image of a panda, to us it's obviously a panda, so we can see that, and you add a tiny amount, I think this is 0.007 times this adversarial noise is just amplified so you can see it, and add it to this original image, you get something that's classified by most state-of-the-art algorithms. So pretty much anything you would have seen or heard today, Inception, ResNet, all of them have this flaw in different levels, but all of them suffer from this problem fundamentally, that you can get something to misclassify as obviously not a gibbon, right? But that's what the network thinks, which with much higher confidence than the original prediction. And this is a tiny amount of noise. You can actually run it on your own. I create a collab, like a Jupyter notebook, that you can run this on your own, kind of on your own machine. It's kind of surprising how well this does in fooling those computer vision algorithms. Like, you can have this image from some data set, and you can print it out. So even it survives the transfer into real world. So the clean image, it gets classified as a washer with 53%, 54% accuracy. But you can make the network think it's safe with and not a washer with 40 or so percent accuracy, which is kind of terrifying, because these are literally have been images from the original data set, then printed out on a piece of paper, then you put the convnet onto a phone, you basically run the neural net on a phone, and you take a picture of the piece of paper, and it still fools the algorithm, right? So this is kind of a insufficiently sort of explored space in many domains. It doesn't matter as much as you might think initially, but if your application has certain mission, it's security critical, then you should really think about what adversarial examples and adversarial attacks do to your computer vision system. So obviously, the reason why this even works is that this noise has to be very specifically selected. It's not just any noise, right? It has to be selected. In fact, you kind of abuse stochastic gradient descent, and rather than by minimizing the loss, you try to maximize it. So rather than going downhill, you go uphill. And basically, because there's so many more ways to be wrong than to be right, it's actually quite easy to fool the neural network. So obviously, there's many technical reasons for why this happens, but at the end of the day, I think the sensible takeaway from this is not to be completely freaked out, because obviously this looks flashy and is an interesting academic problem, but in the real world, a lot of the time, this does not make a massive difference. There's many propositions, and academics love this stuff, but the problem is that a lot of applications, if you have this vector of attack, you probably have much simpler vectors of attack too, right? Rather than making an adversarial stop sign, that, you put some adversarial sticker on, why not just like, push the stop sign over? If you have access to the stop sign, why does it matter that it has to be sort of like some weird sticker that you put on top of it, right? You have to like think about what the vectors of attack and where do you actually use this, because this is not easy to generalize and deploy. Like you need some really specialist deep learning knowledge to actually do this type of thing. But at the same time, there's a challenge of like modern machine learning is kind of wrong almost everywhere, except for where we train it on the training data. So it's interesting to think about what does that mean for training your own algorithms. And in fact, adversarial examples have been identified in text, in even in obviously most of computer vision, and even in humans. So we get some adversarial examples which kind of fool us under certain conditions. But yeah, I mean, this is super easy to replicate. Like this is something that I've done a couple of months ago just to see, like, these is just like randomly selected noise, and you get like misclassifications as real objects. So this is not the sort of best network you could use, but this was the first network that achieved allegedly superhuman performance. So kind of makes you think. Yeah. So again, this is one of the papers that people like propose, like these stickers that kind of look like they're just some art, but actually they're adversarial examples. But like I talked about, like there's usually simpler vectors of attack than just like using adversarial examples. There's a lot of complicated reasons for why this happens. I don't think I have really time to go into that. But generally, it's I think the key takeaway is like if you have access to the model and the model weights, which you have to, right, for this type of thing, like you almost have to know what gradients there were and what, you have to have access to basically the actual deployed model to make this work. Then if your attacker can somehow get that, then that's a much bigger problem. That's probably the problem you should solve first rather than trying to solve adversarial examples. So, okay, a lot of this was mostly theory. So let's now talk about some adversarial examples. Though, of course, generating pictures of cats from big GAN is practical application in itself. Okay. So one of the things that's interesting. So, for example, going back to cycle GAN, you can have something that you take like satellite imagery and you make something that looks like Google Maps, and you can make a satellite imagery back again, which is useful both ways, right? Like because this translation allows you to create Google Maps much more quickly, and this translation allows you to visualize what a city might look like based on the layout. Some people used it for design, so some people use it to generate logos, and some of them look quite good, I'd say. There's this thing called Discovery GAN. This is actually kind of old now, it's 2016 or so. And you basically like learn to basically match the style of like a handbag, to like a style of a shoe. So you can kind of like transfer what would be the like nicely fitting, collection item with it, right? So if you want to have like, shoes that go with your handbag, you can just kind of run it through a GAN, and then you're fitted out for the day. So this is something that from my own research, like I try to basically create like synthetic examples. This is from something that could be a video game, but it's actually like a fairly standard data set. Obviously, this looks a little bit crappy, and you can tell that these are like computer graphics. And then on the right here is something that's the same image, but the domain transferred to look more photorealistic. So you can still kind of make out that the cars are the same. Sometimes it kind of makes some things disappear, like the bike's not longer here. I think actually they're not exactly perfectly aligned, but this is the same scene. You can still see the geometry, so you can kind of like make it transfer the synthetic domain into something that looks more realistic. And I think we'd agree that this kind of, at least in the first glance, looks like this could be a real scene, but it was actually generated. Other applications, so there's this really interesting work from NVIDIA that came out earlier this year. That basically you draw like a semantic map of what you want to generate, and then it synthesizes that image for you. So you kind of draw the beach here, and then it understands that this would probably need to all change. So like adjust the rest of the image. You know, these are like interesting like artistic applications, or you can do sketches very quickly. You know, but it's actually you know, a real important change. Also, I think this particular implementation even has pre-trained models. So if you want to run it on your computer with a little work, you can try and see how well it does. Obviously, there's a lot of other people like they're really excited by this. So again, I think this is work from NVIDIA, and you just as an input here, you kind of take just the label segmentation, so just like the description of what object should be where, and then you can prime it with a single image, single still image, and it'll generate that entire sequence in that style, right? So if you want that something that's like LA, then you can just give a single picture of LA, and it'll render this entire sequence as LA. Or you want to drive in Berlin, you can do that, or New York, or whatever. So you can kind of synthesize different use cases based on the same input segmentation and a single image, and you can get a video out of it, which is quite cool. There's more practical applications in synthetic data generation. So if you have like a severe class imbalance, so some of my friends like Kieran, that they're basically using this, to generate new types of, or synthesize more data for the rarer cases of breast cancer. So obviously, you know, it's a class imbalance problem, which is good that it's class imbalanced, but at the same time, your machine learning models are not going to work super well because there's obvious massive disparity between the two classes. So if you want to have a better performing models, you can synthesize new data to improve the accuracy of your classification network. Obviously, like if you have like algorithms that generalize poorly, you can kind of add in more data from, let's say, you know, if your self-driving cars don't work super well in LA, you can add more synthetic labels from this. You know, if you don't have enough data at all, you can sometimes use GANs as well. You can just synthesize the data from scratch, but that's much more complicated. People have more exotic applications, can be like in 3D generation. So people have done this. I mean, it doesn't work extremely well, but it's a good first step. Again, this field is relatively new. You know, there's obviously digital asset creation, design, architecture, engineering, lots of other interesting papers. I won't go through this, but just as a list of like something that just from the top of my head, things that I've seen GANs applied into, like it's everything from image synthesis, sketch suggestions, style transfer, cryptography, natural language processing, text to image, super resolution, image hard. I won't read this, but like, just know that there's a lot of different fields where people have like been excited by this. In context, like GANs have had a massive explosion. I think it's very rare to see something that's really took off as much as GANs did. Like when you think about most machine learning, has its academic roots in like the 1997 and 1998 papers, whereas GANs, genuinely the very first papers was in 2014. And it's like now over 10,000 citations. Like it's crazy. There's a couple of AI celebrities that think it's kind of important whether or not you believe them. I guess that's your judgment call. And then obviously like GANs have had like 2.5x the number of citations that original TensorFlow paper has, which I think speaks volumes about that people are really excited about this. The business applications are still relatively young. But partially because it's a new technology, there's lots of challenges. I don't know if I have time to show this video. There's this really cool, like, yeah, okay, I'm being told that I'm running out of time. So I won't show this, but if you want to Google it, but super important practical applications of GANs is that it makes nerds look cool. It's called Everybody Dance Now paper, and basically make you dance to any song as if you were like a total pro. So that definitely, if you want to improve your dancing skills, or at least your synthetic dancing skills, definitely recommended. There's some references if you want to take a picture, and I'll actually leave this. Yeah, and I think that's kind of everything I have time for, so probably we'll move on to Q&A. Oh yeah, the book, if you want to check it out, and if you want to talk to me about synthetic data sets, here's my email. That's it.